Thanks, everyone. So it's actually great to be back at OSFC. This is one of my truly favorite conferences. This conference had a tremendous influence on us at Oxide. So OSFC in 2019 was the last conference that I actually attended in person. So it's fitting that my next conference was OSFC 2022. I think if I could go back to myself in 2019 in a time machine and try to explain what happened, I don't think I would believe any of it. Not least, of course, the pandemic and everything else, but also to be back in front of this crowd, to be with this crowd. And I was so invigorated by what we saw at OSFC 2019, had such a tremendous influence on us, and talking to folks like Ron, meeting folks like Trammell. We did our On the Metal podcast series, which is a series of interviews with interesting technologists. Many of them came from OSFC. So if you listen to that series, OSFC comes up again and again and again. So this is a terrific conference. It's an honor to be able to speak here. It's great to see so many familiar faces and new ones here. But with that said, I have to tell you that I have come to bury the BIOS, not to open it. So I want to talk about the need for the holistic systems. And by that, I actually mean the need to reintroduce holistic systems, because in the beginning, systems were all holistic. And what do I mean by that? A holistic system is one in which we are designing the entire system, where we are thinking about the hardware and the software together. And that's the way we used to do it. That's the way we used to design everything. And the hardware and the software came together as a unit, and it was delivered with the computer. When you bought a computer in the 1960s, in the 1970s, you had all of the system software necessary to run that computer. That was the good news, and that those things were definitely co-designed. But that co-design had a lot of problems, because it meant that every new hardware project also was very often a new software project. And the results were kind of predictably disastrous. So if you read the Mythical Man Month, which is all about the development of OS 360, where very much new system software, new hardware, and new programming language, and disaster all around. It took them much longer than they thought it would. But then we had a very important innovation at the end of the 60s, going into the 70s, where we began to break system software away from its hardware bonds, where we began to make system software truly portable. And I don't know that Unix was necessarily the first system to become portable, first system software to become portable, but it was certainly the first one to become widely available, first portable system to become widely available. And so there's a reason that Unix really caught on. Unix caught on because we were, now you could actually have the same system software run on a new machine architecture. You didn't actually have to rewrite the operating system every time you invented a new machine. So Unix, for very good reason, caught on everywhere. And now every computer manufacturer had its own Unix variant, and it's definitely fueled the mini computer and workstation boom. And there was many variants, and these variants were still co-designed with their underlying hardware. So there was you still had, to varying degrees, co-design occurring, and these were still holistic systems at some level. And in some regards, it was a sweet spot, and you had these holistic systems, but you still had enough commonality across them. They were broadly similar. But of course, they were also very different. And anyone who had to support many different Unix variants can rattle off all of the ridiculous differences between them. I myself still do not know the order of arguments to bcopy. Because of memcopy, I have been completely corrupted, and am never able to retain the actual, because one has the source first and the destination second, and the other has them inverted. I actually, to this day, can't tell you which one is which, in part because I, probably like you, refuse to kind of like freewheel that one. You don't want to just like, oh, I'm pretty sure the source comes first. It was like, I'm going to go back to the man page, just like look at the man page. But because I go to the man page every time, I never retain it. And now I write in Rust and don't do memcopy anymore. So I think I'm going to die not actually knowing the proper order of arguments, memcopy versus bcopy. So there are a lot of these little kind of differences. There's also a much bigger problem, and that is that these Unix variants were all proprietary. And this was really unfortunate because it was antithetical to the ethos of Unix. Unix was a very important innovation in many different dimensions. One was its portability. It was really the advent of modernity in terms of operating systems. But another was this idea of sharing source code. It was a very kind of academic idea. Of course, if you want to have an academic idea that's not perverted, don't invent it inside the walls of the phone company, because AT&T unfortunately went to war with everyone who was using Unix. We had the Unix wars of the 1980s and early 1990s. It was the Unix wars that really paved the way for Linux, because everyone else was distracted fighting one another. Poor BSD was distracted with an empty number of lawsuits. So it is very, very unfortunate that these things were proprietary, because the fact that they were proprietary really prevented cross-pollination of innovation, and it meant that the underlying hardware systems themselves could also remain proprietary. And as we know, and the reason we're all here is because we really deeply believe that open source and open systems are a very important innovation. So Unix was great in a lot of ways, but there were also a lot of problems. Elsewhere, we had homebrew computing, right? Elsewhere, we had while Unix was kind of happening inside of academic and corporate walls, you had the microcomputer movement and you had the homebrew movement. And really pretty interesting in that there was now an explosion of hardware. There is no real dominant vendor in the 70s. I mean, pity the poor folks developing system software in the 70s or application software in the 70s. There's a great video, if you can find it, of Rob Barnaby, who's the software engineer you may not have heard of. He's the guy who wrote WordStar. And WordStar was written completely in assembly. And it was written for a bunch of different architectures. And WordStar had to know everything about absolutely everything. It's just wild to try to develop application software when you've got floppy drives that have got different parameters that you need to use and so on. And you don't even have like device drivers that you're interacting with. So and if you look at the dominant system of the time, was CP/M, and indeed everyone assumed that it would be the dominant system for microcomputers, but then of course that future was fumbled to Microsoft. But in the mid-70s, CP/M was the dominant system, and CP/M quickly saw the need to we're having to support this just Noah's Ark of garbage. I mean, I guess it wasn't thought of as garbage at the time, but it's like this kind of Noah's Ark of crazy hardware. And how do we kind of structure CP/M to be able to support this? And their version of a hardware abstraction layer was the basic input-output system. And that's the birth of the BIOS. The BIOS starts with the microcomputer movement and CP/M. And sorry, ignore my notifications. Thank you, Open Source Firmware Conference. Good, I'm glad I'm here. And the presence of the BIOS, and the BIOS was the separate kind of binary module, and that allowed it to be delivered independently. And this is kind of Eve biting the apple. This is like the original sin of firmware, is this separation, which feels like it's so well-intentioned. It's probably even a good idea to separate these things out. But once you separate them, then your hardware vendor can actually deliver this BIOS completely separately from the system software. And this is the birthplace of this very pernicious divide. Now, this is very much not a holistic system. And now you have one group that is actually delivering system software as part of the hardware, and another group of people that are delivering the actual system software that's going to run on top of the hardware. And this became standardized as what became known as the system BIOS, what we would now call the BIOS today. And the IBM, the PC era, very much codified this split. So if this split was starting in the early 80s, it was sedimented, and by Compaq in particular. Compaq rose to dominance because Compaq took advantage of what it could see was a real thirst for a standardized software market. People wanted to be able to generate software that could reliably run on other people's computers, which is a reasonable thing to go do. And the way they did that was by really enshrining the BIOS. And Compaq, almost more than anything, is innovation with respect to firmware, more than anything else, and really getting that BIOS to be solidified and really emphasizing compatibility. That's what Compaq was really able to do in that era. And not necessarily the wrong thing to go do, I suppose, but boy, it really sedimented this divide, because now the BIOS was really part of the computer. And now you had the system software split into two: the part that was delivered with the computer and the part that was delivered by the system software provider. And that system software provider increasingly became only Microsoft. And as it became only Microsoft, the hardware vendors sought to serve only Microsoft. And we are now entering the late 80s, mid 90s, 1990s, which I think is an extraordinarily dark era. Now, this is when I grew up. I'm a Gen Xer. So, I was coming of age in the mid 90s. Like a good Gen Xer, I believe that my adolescence sucked. And I believe that adults didn't know what they were talking about. And I feel like I'm, again, a classic Xer. So for a while, I thought, like, well, maybe the 90s didn't suck. I'm just an Xer, so of course I thought they sucked. In hindsight, they definitely sucked. And I feel I can defend the fact that they sucked. And it was a very, very proprietary era. And it felt suffocating. All software was proprietary, effectively. You had Microsoft was really the only operating system of choice. And in fact, in the mid 90s, it was a foregone conclusion that Microsoft was going to run absolutely everywhere. And in one of the most embarrassing moments in the history of American innovation is every single American computer company mortgaging its future to Microsoft, with the exception of one, Sun Microsystems, and that's why I went to work for Sun in 1996. Sun was actually the only computer company that actually believed in independence from an OS perspective. Everybody else was trying to mortgage their future to Microsoft. It was a dark, dark time, and I say that not just as a Gen Xer. But it got worse. And we heard in the earlier talk about the peril of SMM. SMM, I mean, even the very name is obnoxious, the system management mode. It's like the operating system exists to abstract the hardware. Why would there be some other mode to manage the system? It's like, no, this is the operating system. Who are you? It's like, well, as it turns out, you are this hidden mode that executes, that does whatever you want, whenever you want. And it can't actually even be detected by the operating system. Who is in control of the computer right now, actually? And the problem is that we actually don't know who's in control of the computer. This is the problem with SMM, is that SMM believes that it is in control of the computer, what the operating system believes that it is in control of the computer. They actually operate at cross purposes to one another. This is the exact opposite of a holistic system. This is a system divided and at war with itself. And it is a really serious problem. And I think I'm like a lot of technologists, and then when I saw SMM, I'm like, I don't like that. Let's hope it works out. I don't know, maybe it's not as bad as it sounds. As time has gone on, it's actually, it just turns out it's much worse than I would have thought. And actually, as it turns out, we were just backing up the truck and pouring all sorts of software in SMM, because what was happening was SMM became the vector, the BIOS became the vector, the firmware became the vector by which computer companies could ship their differentiation. They couldn't actually ship software. They couldn't ship software in any true sense. So they used the presence of these vectors to ship their value add. And which I don't mean as a punchline, because it could be, and it was in some cases. I mean, it was actually being able to suspend a laptop is nice. Suspending and resuming a laptop is nice. And the way that was done, unfortunately, was primarily through SMM. And well, as long as that door is open, let's start using it for other things. And let's start using it for mouse drivers and everything else. And let's start, now all of a sudden we have this shadow operating system that we can't see, that is very much proprietary, that is running whenever it wants, that we cannot get rid of, we cannot eradicate. And this is really, really problematic. And we've seen in the last couple of years, as we've seen like actual malware that exists in SMM, that no, seriously, this is really, really problematic. And again, it's the opposite of a holistic system. Then enter EFI and UEFI. So we actually had a chance to kind of reset some of this. And maybe all of this would have been irrelevant if x86, if Intel had not executed so well, or if the risk providers hadn't executed so poorly. I mean, I was at Sun, so we were definitely on the executing poorly side of this. I definitely, needless to say, when I looked at a recent Intel roadmap, I'm like, I recognize that. That's a Spark roadmap, circa 2002. That's not a compliment. But Intel executed very, very well. x86 executed very well and out-executed everyone, certainly economically, and became dominant in the server space. And before x86 actually vanquished everything, Intel had bet it all on Itanium. And when they bet it all on Itanium, they wanted to actually take a from-scratch approach, which is great, to the firmware problem. And they actually evaluated a bunch of things. And they had some good ideas, actually. And in particular, a tribute to the folks that were pioneering this inside of Intel. They actually looked to some of the RISC vendors, MIPS in particular in this case, but both MIPS and Sun and other RISC vendors had actually some pretty good approaches to open hardware. And the MIPS approach would have actually been a great one. So the Advanced RISC Computing initiative, if you look at the way they defined firmware, it would have actually, UEFI would have been all right if they had just taken that. There are some things to like about that. It's a little dated in hindsight. Ditto open firmware. There are actually things to like about this. The things that I actually like about this is it puts firmware in its proper place about when it executes and what its role is. Because its role ultimately should only be to facilitate the software that's going to control the computer. And there needs to be one body of software that controls the computer. It really needs to be the operating system. And anything else actually is antithetical to what the user wants and the user expects. So had they adopted some of these other things, I think the world might have been slightly different, but that's not what happened. And what happened is that UEFI really overconstrained itself. And UEFI decided, like, actually, we need to be entirely compatible with everything that has come before it, which meant being compatible with a legacy BIOS. And by being compatible with a legacy BIOS, what that actually meant is we are going to provide facilities for the operating system to call into after we have booted. So we are now going to have code that lives, that can be called into. And it's like, as long as we're going to have code that lives that can be called into, like, maybe we should just be able to, like, why can't we just call into ourselves? Why can't we just assert control of the machine? And UEFI, I think, became the worst of all worlds. It is extraordinarily complicated. Its origins are certainly deeply proprietary. Yes, there are open source variants, but it is deeply proprietary. And it manages to dial up this worst possible compromise of it is isolated from system software in all of the wrong ways, and yet entangled in all of the wrong ways. So it's neither isolated nor a part of system software. And it is become really problematic. And it is now so entangled, in particular, with that very lowest level of platform enablement, like the stuff that's required pre-boot. It is so entangled with it that non-UEFI platforms have actually become effectively impossible in x86. And I agree with I believe it was Simon, the earlier speaker, who decried ARM for adopting UEFI because it is really gutting to watch putatively new platforms re-inherit all of this legacy that they actually don't need to inherit. You actually don't need to inherit this legacy. This is x86's problem. Like, leave x86 over here. You can take a much better approach and solve the problem that you want to solve without reintroducing all these other problems. So it's unfortunate to watch UEFI metastasize into other instruction set architectures that actually don't need it and shouldn't have it. And it gets worse. So the SMM is bad, but it gets actually even worse because of all of the hidden cores on your CPU. And Trammell was talking during the break about a talk that he saw where the speaker asked, how many cores are on your x86? And the answer is, like, actually no one really knows. You know how many, you might know of some, someone else next to you may know of some others, someone else may know of yet others, and someone who works at the vendor may be like, actually, a couple others you guys haven't yet mentioned. There are lots and lots and lots of what I would call non-architectural cores that are not executing application code, that are not executing the operating system, but very much are executing. These are the cores that are responsible for managing I/O, for managing the security of the system. And these cores are, we can't see into them. We don't know the software that's executing on them. We don't know when they execute. We don't know why they execute. And again, we don't even know how many there are. And what this means effectively is that the operating system itself kind of is running on the architectural cores, believing that it's controlling the machine, but actually the hidden cores are actually doing very important work in this unseen work. If you recall, like the opening to The Simpsons, you got kind of Maggie with the steering wheel that's actually like not attached to the car. She kind of thinks she's driving the car. This is to a certain degree the operating system. The operating system believes it's driving the machine, when in fact, the hidden cores actually drive the machine. And the hidden cores have been responsible for establishing the I/O engines. The hidden cores have been responsible for and are responsible for the security of the system. And this is not actually lost on everyone. So I don't know if folks have seen this. This is Timothy Roscoe's Aussie 2021 keynote. I don't often recommend other people's talks in my talks, but this is definitely one to go check out. And this is interesting because Roscoe, and what he's kind of circled here, are some of the non-architectural cores on a particular SoC. Roscoe is kind of calling other academics to realize, like, hey, you think you're running on the hardware and you're not. There's all this other hardware out here, all of these hidden cores that we are not actually executing on. And isn't it time to rediscover that? Isn't it time to rediscover the hardware? And and he calls it a security catastrophe. And I definitely agree with that. I don't think that is shrill. I think that is apt. It is a security catastrophe. But the degree that I completely agree with his sentiment. The one bit that he misstates actually is when he believes that it's time for Linux to discover these things. Linux can't discover these things. The operating system actually can't, because they are not documented. We actually don't know what's running on it. So he kind of portrays this as a retreat of Linux from solving interesting problems. That's not really fair. I mean, that may also be true, but it's not the whole truth, in that even if you are interested in actually understanding what's running on those hidden cores, even if you are interested in having system software that actually that is managing I/O engines, you can't. And you can't because it's not documented. And this is a huge, huge problem. So, okay, let's open source the BIOS. Like, that's the answer. Let's open source the BIOS. Now, to be clear, I am all for an open source BIOS. And I'm all for open sourcing anything, actually. I don't think there's anything on this planet I wouldn't want to see open source. I think open source is just good. Even the source that burns your eyes to look at is still good to get out. Like, let's get it out there. So I think open source is just positive. I would never try to talk anyone out of open sourcing anything. I think it's very, very important. But open sourcing the BIOS is not the answer. And I think when we insist that being the answer, we are insisting on something that I believe is not sustainable. And we have seen that lack of sustainability. When AMD actually open sourced a good chunk of Agisa in 2011 and retrenched on a bunch of that. So it was open sourced, but ultimately abandoned. And it's really challenging for these internal teams to open source their work as they are doing it. And it's challenging for a bunch of different reasons. It's challenging because this is the lowest level silicon initialization. This is often viewed as super proprietary. And now, I think that's like a little bit ridiculous, because I don't think there's any great intellectual property down there per se. Also, like, so let's say you know how the I/O engine is configured on an AMD Milan. What are you going to do with that information other than use it? Like, what are you going to do with that information other than make your software more dependent on the product that AMD sells? So I don't quite get that argument around not open sourcing things. I think the argument is actually more one, honestly, even though they don't say this necessarily, it's one more of fear. And fear of, like, well, we just haven't documented it before, and we're just worried that there's going to be something in there. It's like, well, there may be something in there anyway. Like, your anxiety, your lack of documentation is not what is going to prevent someone from discovering some vulnerability. It's not like we discovered Spectre and Meltdown because someone leaked a doc. right? And in fact, quite the contrary. And they're actually, speaking of oxide, one of our engineers, Laura Abbott, she's very upfront about saying that the latest vulnerability that she found in the LPC55, she would not have found if they had open sourced the boot ROM. Because it was the fact that they hadn't open sourced the boot ROM that caused her to reverse engineer the boot ROM. And as she was reverse engineering the boot ROM, she discovered what appeared to be, unless I'm missing something, a glaring vulnerability, which indeed it was a glaring vulnerability. So actually, if you document things, people are less incentivized, honestly, to find your vulnerabilities. So please, we actually need to get over that. But I don't necessarily think that they're going to do that to open source the BIOS. I don't think we're going to see the teams open source this work as they actually do it. And the problem then is actually not, I think, is not that they're not open sourcing their work. The problem is the presence of the abstraction. The problem is the abstraction layer at which we are building the system. We are, I think, and this is where I do agree with Roscoe, in that we are too content to have our operating systems not actually control the entirety of the SoC. And we actually need to demand that we have the ability to build a truly holistic system. We need a different model. We need to return to a holistic system. We need to return, it's the operating system. Its job is to control the hardware and abstract the hardware. We should welcome adding hardware specificity to that operating system to make it better. That is something we have always done in operating systems. And I think that one of the things that I love about Roscoe's talk, and that I certainly resonate with, when I was coming up in the mid-90s, I was told that operating systems were done. And that didn't feel right to me. That definitely wasn't right. And what Roscoe is reacting to is people saying now that operating systems are done. Operating systems are emphatically not done. We've got a lot of work to do, but this has always been true. It's hard work. It ain't easy. But what we need to do, I believe, is that operating systems need to be willing to take responsibility for these other cores on the SoC, and they need to be willing to manage the entire SoC. We need to not rely on vendor-provided code to boot our operating systems. The vendor should provide the part. The vendor should provide the documentation. We collectively, all of us, should provide the systems, the software systems, to actually boot that. And history shows us that because we are biased to making those systems open source, we are biased to sharing them with one another, we will generate better software artifacts as a result. So this was kind of the belief that we had, the challenge that we had for ourselves at Oxide. So just to give you a little bit about Oxide, we're developing a rack scale machine. So we had observed, and again, this is kind of at OSFC 2019, we had observed that the machines that one could buy from the likes of a Dell or an HP or Supermicro looked nothing like the machines that the Googles and the Amazons and the Facebooks, now Metas, were building for themselves. And we thought that the world should actually be able to buy a rack scale machine. And the beauty of actually taking this approach is, and we kind of knew this at the time, is that we were taking a clean sheet of paper. And boy, if you're going to take a clean sheet of paper and you've managed to coax some venture capitalists into investing in you, God bless Eclipse Ventures, thank you. If you're going to take a clean sheet of paper, take a clean sheet of paper. And let's go solve some of these problems. Let's go solve some of these long-standing problems. And up and down the stack, we wanted to take a big swing and solve some hard problems. So let's clean up some of this baggage. And indeed, many of us are at Oxide, and myself included, because we kind of view it as humanity's last best shot to undo some of this legacy of the last 3 decades. So let's start with, and we saw a great talk earlier this morning about the BMC. Cannot say how strongly I agree with that. BMC, goodbye. Let's get rid of the BMC. This traditional BMC controls far too much. It's the computer within the computer. It is rife with vulnerabilities. The root password, actually the root password, the ASpeed's root password was our Wi-Fi password at Oxide. A little BMC humor for you. We actually had to change it because someone had errantly leaked that on the internet. So I regret to inform you it is no longer. But you know, again, with the right audience, that joke kills. Anyway, we want to get rid of this traditional ASP BMC or its Nuvoton equivalent. and replace it with what we should have had all along, which is a service processor, which does the things that you actually need to do, which is really like power management, thermal management, maybe some modicum of inventory management, and like that's kind of it. Serial console, that's it. You don't need to have VGA and USB and all this other gunk. You just do not need it. So we got rid of the traditional BMC, replaced it with a service processor that's based on an STM32H753. We've got our own root of trust on there, despite its vulnerabilities. LPC55. There's a great podcast with Laura asking. Laura has found not one but two vulnerabilities in the LPC55. And the interviewer, great interviewer, was like, out of curiosity, like, why are you still with the LPC55? Like, why are you in this bad relationship? It's like, well, secure silicon is hard, as it turns out. The LPC55 is the best of a bad lot. Secure silicon is hard. Both of those run our own operating system, Hubris. I recommend, if you haven't, Cliff Biffle gave a terrific talk at last year's OSFC on Hubris. Hubris, so named because it's our own operating system, because we had the hubris to do our own system. I did the debugger for Hubris, which of course is humility. Seems appropriate. And so we got rid of the BMC, and as soon as you get rid of the BMC, you are committing to doing your own board design. So we had this kind of idea, naive idea. This is one of the things I would probably not want to tell 2019 Bryan, because I worried I would like lose my resolve. But I kind of had this idea when we started Oxide that like, well, we'll get rid of the BMC, and that's going to mean like tweaking some designs. And I kind of cringed when I think about the number of times I talked about tweaking existing designs, because as soon as you get rid of the BMC, it's like all of this hair, all the hair kind of comes with it. And it's like fishing a tire out of the river. It's like everything is stuck to it. And it's like once the BMC is gone, you are doing your own designs. And so we did our own board design. And that was, if we made a mistake at Oxide, it was not embracing that we're going to do our own board design early enough. We've done our own board design, and boy, do we not regret it. We've done our own AMD-based board design, based on AMD Milan, and we've done our own switch and a bunch of other things. But the question was, can we actually, as long as we're taking a clean sheet of paper, can we actually develop a truly holistic system on x86? That was the challenge in front of us. And I want to do some quick asides. So it is based on AMD Milan. So one of our big beliefs at Oxide is that we are not trying to pick everything. We're trying to be very opinionated about what we build. We built on AMD for a lot of good reasons. So we're going to go into some AMD details. So the PSP is the platform security processor. This is one of the non-architectural cores. This is the first thing that actually boots and does system initialization. It actually does DRAM training. I was talking to someone earlier who's like, that makes no sense. Like, why? What does DRAM training have to do with security? It's like, nothing. Move right along. The DIM training is just, the DIM training is done by the PSP as part of the Agisa bootloader. So the ABL is the first thing that executes. It does DIM training. The advantage of that is that you come out of there with DIMs trained, right? So you actually don't need to have other software that trains DIMs, which is nice because that's actually very gnarly and platform specific. So the SP actually puts the PSP payload into SPI, brings the CPU out of reset. It then actually executes, and then it jumps to the first instruction on the bootstrap core. Historically, that first instruction coming out of the Agisa bootloader, that's the reason it's called the Agisa bootloader, is Agisa, right? This is AMD's generic encapsulated software architecture. Acronyms that contain acronyms. Agisa is what actually does the platform initialization. And Agisa is effectively PEI for UEFI. And it is designed, it is very much designed to implement UEFI. We didn't want any of that. An AMD CPU has never been booted without Agisa, to the best of my knowledge. And indeed, AMD did not actually think it was possible to actually boot their own CPU without this firmware, which we learned after we had actually booted. So we have to actually in order to do this, part of the reason that AMD thought this was impossible is because any software that's going to not execute Agisa needs to do all of the initialization that Agisa performs. And there's a whole bunch of stuff. This is where you're talking to all of those hidden cores. And you are sending messages in a bottle to go configure PCIe, go configure the DXIO engines, to go the NBIO PCIe strapping. There's a whole bunch of stuff that needs to be done. And this stuff is not really well documented. So this stuff is really pretty painful to figure out. And it's, again, historically been done entirely by the CPU vendor, not very thoroughly documented, often not documented at all. So that's kind of challenge number one. Challenge number two is that the actual payload is really size constrained for reasons, and it's size constrained to about 13 megabytes. So this is a challenge because you in that payload, you only have 13 megabytes. What are you going to do in that 13 megabytes? And it's reasonable, and indeed many do take what I would call a stage-based approach, where it's like, okay, in that 13 megabytes, I'm going to have a bootloader, and that bootloader is going to actually boot another system, another operating system. And that's fine. The problem with that is it necessitates a pseudo reset of the system. So and we call that going backwards. So anytime that software passes off control to another body of software that believes that it is on a reset system, you are going backwards. And we could not get the confidence that we could reliably go backwards on AMD. And it's very hard to get that confidence, by the way, that you can go backwards. Now, not to say that people don't do it, not to say it doesn't work, but we could not get the confidence that we could reliably move the system backwards. We wanted to move the system only forwards, so we actually don't want to ever reset the system. So when we actually pass control to that body of software that executes out of the SPY payload, that body of software is the operating system kernel that then goes and gets the rest of itself from SSDs. So in particular, we've got enough to actually boot the kernel. We're missing a bunch of user land, a bunch of other stuff, but we actually have enough in that little payload to be able to actually pull in the rest of the operating system. So those are the two challenges. I think if I've got time, I'd like to show you a demo. Demos are much better than slides, I think. I think we can safely agree on that. So this is, I am logged into a system that is in Emeryville, California. So excuse the long latency. This is one of our Gimlet sleds. So this is, again, AMD Milan, single socket AMD Milan with a terabyte of memory. And what I'm going to do is I'm going to send this thing into A0. It's in A2. This is just a little internal tool we have that's showing us a bunch of stats about what the system is doing. And while I'm doing that, I'm actually going to bring up the console here. So this is where and I'm going to give you a little tour of hubris and humility here as well, if you want. But we're using actually our debugger to execute a console. So this is a serial console, and right now we are in ABL. We're in the Agisa bootloader, which is the reason that we're not seeing anything here. If we can actually see that, and actually you can it's kind of mesmerizing to watch this stuff boot by watching its power draw. So you can actually see, like, and you just saw the memory pop up here. On EFGH, and ABCD also probably popped up. So this is, it may be hard to see on the screen here, but the power draw of the VRs that are connected to the DIMMs popped up as this thing is now training its DIMMs. So what this thing is doing is DIMM training, which is total art/science, where it's trying to figure out what are the actual values that I need to plug in for this particular DIMM, given its location and given what I kind of observe. It's kind of amazing that memory works at all, by the way. This is a persistent theme at Oxide, is I can't believe that any of this works. I mean, the amount that I did not understand about a computer, by the way, like every day I think, like, okay, today is the day that I finally learn how computers work. It's like, no, it turns out that's going to be tomorrow, for arbitrary tomorrow. So forget it. So this thing is training DIMMs. We may actually see that it is, there we go. So we are now at the banner. We are now actually booting the system up. So yeah, sorry, it boots a little too quickly. So that's once we got out of the ABL, it boots pretty quickly. This is scrolling back. This is the actual, the Pico host bootloader. So we actually do have a very, very small bootloader. All this thing does is shunt control right into the operating system. So that thing is written in Rust. That jumps into the actual operating system, and you can see it giving you all the information about all the straps that it's writing. You can see this is very much still a debug system because we've got a warning, we're out of here. I assume that that's a fine thing. I haven't gone into that one. I assume that's good news, not bad news. I do love, like, the question marks, like, DXI devices successfully trained? Yes, it appears they are. And then we're configuring devices and actually bringing the entire system up. I believe that this is a Star Trek reference, but I don't watch enough Star Trek to actually know. And now the actual system is all the way up. And so this is an actual like full system. This thing is now, everything is up on this thing. This is ready to actually go provision VMs and do everything it's going to do as part of the control plane. So what you are seeing is a system that has booted without a GISA whatsoever. And again, has not been done before, to the best of my knowledge, which is, again, kind of a tragic reflection on humanity. But we believe that this is, so we've managed to achieve this. We've done it with a pretty small team, albeit one that's very dedicated. We believe that other people should take this approach. We don't believe that everyone should take this approach. I think that there are other approaches that are valid for other folks at other times, but I think it's in all of our interest that some of us are taking this approach. Because by taking this approach, we are forcing the system to be documented and to be understood. Everything that we are doing is open source. You've already seen us open source a bunch of stuff in terms of hubris and humility and our control plane Omicron and Helios and all of its surround will be open source when we actually ship our racks. So that and actually blocked on our vendors for that, but we'll get that out there. So we think that holistic systems have really clear advantages in a bunch of different dimensions. I will tell you that part of the reason that I got here is in a previous life, deploying a cloud on traditional commodity infrastructure and having an absolute pandemic, and in the pre-pandemic sense, of DIMM failures, seeing DIMM failures in one data center. We were seeing DIMM failures all over the place. And it was really vexing because we were not seeing any correctable errors. We were just seeing fatal failures. Now, fortunately, well, I guess an advantage of having been at Sun in the bad old days, I know all about memory errors, and I know all about where they come from. If you're a Sun customer of a particular vintage, the eCache parity error still may make you twitch, maybe you weep a little bit. Certainly I do. But I learned a lot about what causes memory to fail, and uncorrectable errors do not come out of clear blue sky. Uncorrectable errors, you always have correctable errors that predate uncorrectable errors. We couldn't get to those uncorrectable errors because the correctable errors because the firmware was eating them. And the firmware was eating them deliberately because it is the firmware first model. I'm not joking, that is capital F, capital F. It's like a firmware nationalist movement. The firmware first model has it eating errors. You cannot deliver a reliable system when the operating system does not know what's happening to its DIMMs. When there is a house fire in its DIMMs and the operating system does not know, we cannot deliver a reliable substrate. And that is the beginning. There are many, 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 many reasons why we know that to deliver a reliable, manageable, secure, certainly, system, we need to be able to deliver a holistic system, understand it top to bottom. Based on our experience to date, this is challenging but possible. People would have said, I think when we started, I heard this from a couple of folks, that it simply was not possible. And again, we didn't quite realize from how thoroughly AMD believed this until we actually booted. They're like, wait a minute, you booted? Like, yeah, of course we booted. Like, you knew we were going to do it. It's like, no, but no, we actually just didn't think you were going to do it. Because other people had tried and failed, but that in part of the reason that they had failed is because the documentation wasn't available. We have to get these parts documented. The most important thing that we are doing as a community is getting people to document their parts. And if you go into either Intel or AMD's SoC documentation, and you compare it to the SoC documentation that you get out of like ST, for example, it's a smaller part. Like the H7 is a smaller part, but H7 is not a small part. H7 is a huge part with a lot of different components, pretty thoroughly documented relative to what we see out of AMD and Intel. It is time for our SoC vendors to deliver us the documentation that we need to write all of the instructions on our own computer, please. And these vendors have a lot to gain by doing this. Like, we want you to do this so we can buy your product, right? Is this complicated? Please, we're not trying to steal anything from anybody. All we want to be able to do is buy more of your product. So please, 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 please document it. And provided we can get documentation for these SoCs, Oxide may be the first, it will not be the last, and we believe that other holistic systems are absolutely coming, and it's the right way to do it. With that, thank you very much. I'm available for questions.
So we are a bit behind schedule, but one quick question is fine.
First of all, very nice presentation. So I have one question. What is your thought on porting the same changes on the Intel platform? How would it be possible on doing that?
I mean, that's kind of a question for Intel. I don't know is the answer. It would be, their model is different. You've got the ME that's in your way, and you've got to figure out what to do about the ME. Please,
so-
Intel, can we open source the
So
ME?
if I could maybe ask my question a little deep.
Sure.
Yeah. Do you think that if PSP would have not done the DRAM initialization out of the box, whether the Pico my bootloader that you've shown, right? It could have been literally that small. It could have been need to do your.
Well, no, remember, there's a lot of initialization that it's not doing out of the box. I mean, we're doing all like the PCIe engine initialization is honestly every bit as complicated as DIM training. So if it were not doing DIM training, we would do DIM training. I mean, it wouldn't be the end of the world. So I think in a platform like Intel, where yeah, they don't do DIM. I mean, yes, I would do DIM training in. The model should emphatically be possible on Intel.
Yeah, no, for sure. But I think it would have been like a more like a. Then obviously you need to have a more bigger firmware block or the BIOS typically, right? Because
I'm not sure. I mean, I think you might be underestimating the difficulty of the lift for AMD. This was not easy.
No, for sure.
So I think it would be the real question is to what degree can you get Intel to thoroughly document the things that you so where they've got their FSPs are having conversations with aspects of their part. If you can't understand the conversations that thing is having, you can't do it. And that's why we need Intel to thoroughly document their parts. Yep.
So we have a 15-minute break now, and I bet you can catch Bryan outside.
Yeah, absolutely. Yep. Thank you.